So, last class we have considered a optimal control problem with constant input and constant in the state. That problem we could not solve completely. So, rest of the problem we will solve it now. So, before that we will just recall our problems, that what is this. We have a optimization function, objective function is minimize this what is called the control effort subject to the dynamic equation of the system and initial condition this. Our job is to transfer the initial condition, that 0 1 initial condition, by using a suitable control strategy, so that it satisfy the our input constant as well as state constant to transfer the state from x 0 to final state x 1 T f and x 2 T f is 0, means at origin. This is our problem. So, what we did is this unconstant optimization problem, constant optimization problem, we have now that this is the constant in input side and this is a constant in state, this state x 1 and x 2, which we have written into this form less than equal to form this. So, these two equation in turn we will get 3 equation in turn. From here we will get 2 inequality condition less than equal to 0, and we assume this x of t is differentiable with time. Then in order to solve this problem, we introduce a new state variable x dot x 3 dot t. We have initially 2 state variable, now we have introduced a third variable x 3 of t dot, and that is formed with the knowledge of the constant which is less than equal to 0. From there we have constructed this state equation. This, if you see this one, equation 3 is 0 when all the constraints as specified here for x 1, x 2 if satisfied, then this right hand side of this equation will be 0. If one of the equation, at least one of the constant is not satisfied, then we can write the equation 3 is less than equal to 0 for all t when the constant 5 either it is satisfied or it is not satisfied. Either when the constant 5 either is satisfied or not constant are not satisfied, then it is less than equal to 0 for all t. At least one condition is not satisfied, then it will be less than equal to less than 0. If all condition is 0, then this is equal to 0. Then we specified that boundary condition for the new state variable x 3 is 0 is 0, x 3 T f is 0. Then x 3 t is 0 for all t, that from the equation we can write it this equal to 0 for all t x 3 expressions. Now, what is we have to do? We will form our standard procedure to form a Hamiltonian function. So, h is formed just as before we have discussed earlier. Once h is formed, then next step is our case is del h del x is equal to del h del x will come later, del h del u is equal to 0. From there we got it u is equal to minus lambda of t, this expression, and our constant on the input is the mod of u must be less than equal to 0. So, which in turn from this equation we can write it that mod of lambda of t is must be less than 1, then it will be a input will be less than 1. When there is no guarantee that lambda of t may be greater than 1, in that situation what should be the control input, and that control input we have decided on the basis of that Pontryagin minimum principle. That means, we have to select, you see this Hamiltonian function, that one that Hamiltonian function is here. You have to select that Hamiltonian, that u is associated with lambda 2. Agree, u is associated with lambda 2. Lambda 2 into this factor will come. So, you have to use the choice of u in such a way, so that that function value is becoming, this product is becoming negative. So, on that basis of this, if lambda 2 is greater than 1, then u must be switched on -1, because our control input cannot be more than 1, even if it is more than 1 lambda 2. Then when it is less than lambda 1 -1, lambda 2 is less than 1, then you switch to +1. When it is in between, then you switch to that whatever is the minus of lambda 2. Suppose lambda 2 is less than 0.5 positive, then you give the input the opposite sign of lambda 2. Okay? So, that means minus. So, our set function is, generally the set function is 0 when x is greater than equal to 1, this is 1. When a mod of x is less than equal to 1, x of t is same x of t. When mod of x of t is less than -1, it is -1. That is the set function, is nothing but a this type of function, saturation function. This is 1 and this is -1, and when this is also 1, slope is 1. When this, if you can say that this is x of t, when x of t greater than or equal to 1, the output, that this is, you can say y of t, the or the such one output will be 1. When this is less than -1, that output will be -1. When it is x is in between -1 to that will be the value of x we have to consider that this is. So, in fact, this is nothing but a u star. If you see this one, u star is nothing but a minus of set lambda t, lambda 2 of t. This is, we can write it that. You see, when it is 1 greater than 1, this is minus. So, minus sign, when it is a mod of this less than equal to 1, that this is the your x of t, but it is minus. So, it is the opposite minus of set function, this indicates. So, then what you did it, that our first condition is del h differentiate with respect to u is equal to 0. From there we got it u star is equal to minus lambda 2 of t. Then another state equation we will get del h del lambda t is equal to x dat. From that we got the 3 equations. Agree? There are 3 state variables are there, including the new state variables. Then co-state equation del h del x of t is equal to minus of lambda t. So, again we will get 3 equations. Then next thing is we have to use the boundary conditions, agree, to solve these problems. And x 1 of t we know which is 0 is given in the problem, x 2 of 0 is 1 as is given in the problem, but our that initial state we have to drive to a origin with a suitable control action, keeping in mind that input is constrained and the state also constrained as given in the problem. So, our final state is x 1 t is 0, x 2 t f is 0, and x 3 from our boundary condition of x 3 is 0, x t f is 0. And another boundary condition from the free end point, if you just consider the free end point, another boundary condition, we will get it, that one. The boundary condition that boundary conditions condition for free end point system is h Hamiltonian function del s of del t, this put the value t is equal to T f into del T f plus del s, this del x t minus lambda of t, that whole T f T is equal to T f, the transpose into delta x f is equal to this. This is the boundary condition free end points of the system in terms of Hamiltonian. Now, you see our terminal cost that S is 0. If you note delta T f is free, delta T f is free, but delta x f is fixed. That means, delta f x is 0 and we do not have any terminal condition x s of 0. So, this term will be 0, whole term is 0 and this term also 0 and we have a this term also 0. We have left with this one is h of t, h of this at t is equal to T f plus minus that one T f that as 0 and this term delta x of this is a fixed. So, this term is 0, whole term will not come into the picture. So, this will be a 0. Then we will put what is the Hamiltonian function and there we put T is equal to T f, that is next step. So, if you write this equation next that our what is Hamiltonian of u star square T is equal to T f, optimum value of the input we have to find out, then lambda 1 T f into x 2 T f plus lambda 2 T f into lambda 2 T f into minus x 1 T f plus u star T f, this is bracket closed, then lambda 3, just Hamiltonian function I have written and putting T is equal to T f, nothing else. So, this is T f delta T is equal to x 1 square T f u s, the unit step function x 1 T f plus x 2 T f plus 1 whole square u s minus x 2 T f minus 1 this plus x 2 T f minus 2 whole square u s x 2 T f minus 2 this is equal to 0. Now, look at this expression this here x T f value is what we want to drive the state from initial condition to the final condition, this value is 0. Then here is this x 1 T f is also 0. So, only this term is there. So, from this one it is a half u star square T f and from there this is equal to 0, this part, then from this part is plus lambda 2 T f into u star T f, and this thing you see x T f is 0. So, this term is not there and when x step, because it is a step input, when x T f 0, this is also 0. So, this is 0 and this part is not 0, but whereas x T f is 0. So, this is u minus 1, that this the step input function is for the value of negative value of this one, it is also 0. This is 0, agree, this is 0 and this is not 0, x T f is 0, this is not 0, but this value, this is also 0, but this there is a minus 2 term t. So, this is also this quantity is, if you see this quantity less than 0, this quantity also less than 0 and this quantity is 0, this quantity is 0. So, this will be the whole part will be 0, whole part will be a 0. So, now our is that one, this boundary condition. So, from there you will see that lambda what is our lambda u is equal to what? Note u T f is equal to minus lambda T f, that is we have our del h dot del u is equal to 0. From there we got it this one. If you put this, so this is the equation of this one. Our last equation, if you recollect, this one was that equation number 8 or 9, just check it. So, our last equation, anyway, this is the equation. From there you put it, that is lambda 2 T f square plus minus lambda 2 T f square is equal to 0. This is the lambda T f is the lambda 2 square this. So, that's lambda 2 T f is equal to 0. Now, we can solve these problems. We can solve this problem by considering our boundary initial conditions of this one. What is this one? You see from the basic state equation, that our state equation we got it x dot, when you are doing that what is called that x dot of t is x 2 of t, then x 2 dot of t is equal to minus x 1 of t plus u star of t, which is equal to minus x 1 of t minus lambda 2 of t. That we got it, if you recollect this one, that you got it from our state equation, that this one. If you see the letter del h del lambda is equal to that this equation, these three equation, and you see we have to keep our state into inside the constraint. So, if you put inside the constraint this, then this quantity is 0, this quantity also 0, this quantity is 0, the lambda x 3 dot is equal to 0, and this value is remain 0 for all t, as we have considered the boundary initial and boundary condition of on x. So, we need only these two equations. So, that two equation you have write in. So, this is the state equation we got it from del h del lambda of t is equal to x dot of t. From there we got it. Agree? Now, and x 3 dot, if you write it, you can write it is equal to 0, keeping that x 3 of 0 is 0 and x 3 of T f is equal to 0. So, this x t is 0 for all the time x 3 of this. So, you need basically these two equation. Then co-state equation, if you see the co-state equation, we also got three equation in terms of lambda 1 dot, lambda 2 dot, all these things. And our co-state equation finally we will get it, lambda 1 dot is equal to lambda 2 of t, lambda 2 dot is equal to minus lambda 1 of t. And now, the third equation of lambda is lambda 3 dot is 0. So, now you see this two set of equation, and lambda 3 dot is equal to of t is equal to 0. Now, see this also, now x 1 x 2 lambda 1 lambda 2 dot, all these things are, you want to solve x 1 x 2, then it is you must have a information of lambda 2, then only you can solve it x 2. Agree? So, how to solve this one? So, our initial condition, if you use this one, the solution of these two equations with the knowledge of this and this, our solution is like this way, x 1 of t is equal to twice sin t plus half lambda 1 of 0 into sin of t minus t cos of t. So, this is and this is this one minus lambda 2 0 t sin t. Solving this and this, we will get it x 1 dot is this and x 2 of t. Similarly, you will get 2 cos t, then half lambda 1 0 t sin t sin t, then minus half lambda 2 0 sin t plus t cos t. So, this is the solution of x 1 and x 2, and lambda 1 and lambda 2 solution we will get it lambda 1 of t is equal to lambda 1 0 cos t plus lambda 2 0 sin t, and lambda 2 of t is equal to minus lambda 2 0 sin t and plus lambda 2 0 cos t. Agree? So, this now you see we cannot solve x 1 until unless we know the lambda 1 0 value, lambda 2 0 values. Similarly, x 2 also. So, lambda 1 0 value, lambda 2 0 value, we must know it. Agree? So, how to solve this equation? So, now and we have a one boundary conditions also there. If you see this boundary condition, we got it lambda 2 T f is equal to 0. The boundary condition, Hamiltonian boundary condition, free end point boundary condition, we got it that one. So, now we how to solve this one? You must know that these are two unknowns are there, x lambda 2 0, lambda 1 0, lambda 2 0, and you do not know that what is called here also lambda 1 0, lambda 2 0. So, find next is find lambda 1 0 and lambda 2 0 and T f, because you have to drive this state from initial condition 0 1 to final condition 0 0 in time T f. So, T f also you unknown. So, how to solve? So, using this end condition, what is this end condition? This is one end condition, another end condition x of 0 or x of 0 is equal to 0, x of 2 0 is also 0. So, now use x of 1 t is equal to 0 this equation. So, let us call this equation number is some equation number is A, this is the equation number B. Agree? Using t is equal to 0 in equation, using t is equal to 0, x 1 0 is equal to 0, x 2 0 is equal to 0 in equation A and B, we get two equations. Agree? So, another equation we will get it at t is equal to T f, we know. So, so you put the value of A 1 that this condition is A and B, this we know x of t x 1 0 is 0 and x 1 this or not 0 at t is equal to T f, at t is equal to T f we know t is equal to T f, this x T f is equal to 0, x 2 T f is equal to also 0. Agree? Using t is equal to T f this. So, in equation 1 and 2 we will how many equations will unknowns are there in equation 1 and 2? We have a 3 unknowns are there. You see one unknown is there, T f is unknown, lambda 1 0 unknown, lambda 2 0 unknown, but we have a 2 equation. We need another equation what is called that lambda T f, lambda 2 T f values is equal to 0, and use the lambda 2 f value equal, you will get another equation. Agree? So, using T is equal to T f in and x 1 T f, this is T f, x 1 T f, x 2 T f is equal to 0 in equation 2 1 and A and B. In this equation A and B, we will get 2 equation, but 3 unknowns. What is the 3 unknowns? Lambda 1 0, lambda 2 0 and T f is 3 unknowns, but we have a 2 equation. Then another equation I can get it lambda T f is 0, then that means we can write it this equal to minus lambda 2 0 sin T f plus lambda 2 0 cos T f is equal to 0. So, from this equation A and B, 2 equation I am getting, from this is another equation, let us call this 3 equation. Solving these 3 equation, we will get the values of lambda 1 0, we will get the value of lambda 1 0, lambda 2 0 and T f. Then easily we can find out the solution of x 1, x 2, all these things, and also lambda t, lambda 2 t. So, we monitor the lambda 2 when it is the mod of lambda t is less than equal to 1, then we will switch that u of t when mod of lambda 2 of t is less than equal to 1, then we will take u star of t is equal to minus lambda 2 of t. Agree? Then when it is a greater than 1, this is when mod of lambda 2 is less than equal to 1. Then this equal to lambda is equal to minus 1 when lambda 2 of t is greater than 1, then it is minus 1, and you will switch to 1 when lambda 2 is less than minus 1. See that equation according to this, we have just switched this one. If you recollect this one, here this thing we have used it here. Once you know the lambda t expression. So, lambda t expression I can know, once you know lambda 0 to lambda 0 expression, then you know what is lambda 0 t of this. I think this is the lambda 1 of 0, that one, agree, lambda 1 of 0. So, this you can do it, and then you can implement the control that will drive at t is equal to T f, that will drive the initial state to a final state at origin. So, this is all about the your what is called the solution of that optimal control problem with constant input as well as constant in the state, how you have to solve it. So, next we will discuss about the norms. The new topics is a norms, the norms of a norms for vectors, matrices, then your signals and systems, means linear systems, this norm. So, the norms, basically the norms gives an overall measure of the vector, size of the vector, that norms it gives an overall measure of the size of a one vector matrix signal systems, then is systems. This norm is often useful for measuring, for analyzing the growth of numerical examples. That norm we generally use for analyzing the growth of what is called numerical errors involved in the process of iterative process. Okay. So, let us call the norm of a vector, norm of vectors. It is often useful when analyzing growth of numerical errors. Let us call how to find out the norm of a vectors. There are different norms, different context it is used. So, let us call, we have a vector, let us call, we have a vector whose dimension is n, which is written as x 1, x 2, elements of these vectors is x n. So, this is a vector is dimension n cross n rows 1 column, and this form a vector space called R cross 1. That means, we can write x belongs to vector space R cross 1 dimension. Okay? That dimension is n cross 1. So, now these are the elements of this vector whose dimension is n cross n 1, and that x 1 x 2 is a constant for the time being, is a constant elements. So, what a definition of P norm of a vector is denoted by double line, whose it is a vector x n 1 by and double line, and this P is defined as summation of I is equal to how many elements are there? N elements are there. So, x I mod absolute value of each element x 1, x 2 dot dot x n, you take it, then to the power of p whole to the power of 1 by p. So, this is called P norm of a vector. That means, how many elements are there? You take the absolute value, sum of absolute value of the elements whole to the power of p, then 1 by p, pth root square root of pth square root of this one, you do it. Now, let us call, most frequently we use the norm 1, norm 2, then it is called infinity norm. So, most frequently we use L 1 norm, which is also called that 1 norm. This is also called 1 norm of a vector, and the symbolically it is represented by x of this suffix 1. This is nothing but a, when you put p is equal to 1, is nothing but a norm 1 or L 1 norm. So, it is nothing but a summation of I is equal to 1 to n mod of x I, this p is 1, or here you can write for p greater than 1, greater than equal to 1, less than equal, greater than equal to 1, or if or you can write it p is equal to 1 2 dot 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 this p is equal to 1 2 3. So, here for p is equal to 1, that it is called norm of a vector. Now, this is you can think of is, suppose you have a set of equation is there, you want to solve it by iterative method, then you the variables are, let us call x 1 x 2 dot dot x n variables are there, you are solving the a set of simultaneous equation. Now, you absolute value of x 1 x 2, whether it is a converge or not here. So, present value of x 1, let us call it is a this E 1 is the present value of x 1, present value of this is the present value of x 1 minus the old value of x 1, this is the old value of x 1, and that is denoted by E 1. Similarly, for x 2, now I am putting I is where is 1 to n. Agree? So, if I take the norm 1 and the L 1 norm, that means one norm of a vector E. E, how many components of E are there? E 1, E 2 dot dot E n, because we have n variables. So, sum of the all errors you make it, and if you less than 10 to the power of minus, let us call 4, then you stop your iterative process. That means, it indicates that all the values, at least it reached to the value 10 to the power minus 4, all the values of E 1 E 2, because I am putting sum of all E 1 E 2 there. So, some situation, if it is a iterative method, norm 1 also they use it. Next is your norm 2. When is norm 2? It is nothing but a p is equal to 2. This is L 2 norm, or it is called 2 norm of a vector, or you can say or L 1 norm, or it is called 1 norm of a vector. So, our 2 norm of a vector is what? This denoted by x 2, this 2, and which is nothing but a your summation of I is equal to 1 to n mod of I this square whole square root 1 by 2. Here for p is equal to 2. This has some meaning, and this is also called, this norm also called is a Euclidean norm, Euclidean norm, or it is called distance. It is basically, if it is a 2 dimensional case, x 1 square plus x 2 square root of this one, and it is nothing but a the distance or length of this vector. Suppose in a 2 dimensional case, if your x 1 is here, x 2 is this axis, if it is this point was x 1 and x 2, and this is nothing but a denoted by x norm of 2. That means, length of this vector is nothing but a Euclidean norm, or the 2 norm of a vector. Again, this is also one can use for what is called to find out the what is called in iterative method also you can use this norm to check it whether the algorithm has converged or not, or this. Next is your L infinity norm, or it is simply called infinity norm of a vector. What is this infinity? Symbolically, it is represented by x is this one, and this when p is infinity, that means in that expression p norm expression, you what you write x 1 to the power of infinity, x 2 to the power of infinity. If x 1 let us say that x 1 x 2 is I told you the numerical value. If x 1 is less than 1, then x 1 to the power of infinity is 0. Suppose x 1 is greater than 1, this is infinity. Out of this, which is x 1 x 2 all these things, out of this which magnitude is the greatest and it is greater than 1, that information is enough to find out the infinity norm. So, the infinity norm I am repeating is max I mod of x I, and I varies from 1 to dot dot n. Out of this, which one is maximum you take, that is the infinity norm of that one. Logic is this one. If you just see this situation of that one, agree? Suppose we have a 3 variables are there, x 1, x 2, we have a 3 variables x 1, x 2, x 1 is less than 1, x 2 is, let us call, is 2, x 3 is 5. Now, you see x 1 is less than 1, to the power of infinity it is 0, x 1 is greater than 1, let us call 2 to the power of infinity, and then it is a x 2 which x 3 which is a, let us call 10 greater than 1, but 10 to the power infinity are also infinity. So, you are what we are considering the maximum value of x y is considered to find out the infinity norm of a vector, this, and you see this power multiplied by the 1 by p. So, this cancelled of this one, if you can think of it, sum of all these things, because basically you make it sum of the all these things, which one is highest you keep it, then you put it highest magnitude of this one p into p, p cancel. So, it is ultimately it is coming max I 1 to t dual absolute value of x I. You have followed my point, this one, this if I write it, let us call x 1, x 2 and x 3, x 1 value is 0.5, x 2 value is 1.5, x 3 value is 3. Then what we will write it, that p values of this summation of x 1 means 0.5 whole to the power of p, 1.5 whole to the power of p, 3.0 whole to the power of p whole 1 by p, this is 1 by p. Now, this is equal to 0 when p is infinity. This is compared to this is negligible, because this is the greater than this one. So, you take it the whatever the absolute value of maximum, that one. So, this and this cancel, only 3 maximum value of from all the components, what is it, that is the infinity norm, that is why you are writing it that one. So, this is the, you call it the infinity norm of a vector. So, next is called the norm of a matrix. Similar way we can define the norm of a matrix. So, first is Frobenius norm. It is defined for matrices by treating the matrix elements, as a vector. Suppose we have a matrix M cross 1 is a matrix whose elements are A 1 1, A 1 2 dot dot A 1 n, A 2 1, A 2 2, A 2 n. We have a m rows are there, A m 1, A m 2 dot dot A m n. This is the matrix whose dimension is m cross 1. So, the Frobenius norm is defined, you that matrices all elements you put it into vector form. That means, this vector, below this one you keep it this column vector, below this one you keep it the next column vector in this. So, whole thing will be vector of dimension n cross, this whole thing will be a vector of dimension m into n cross 1. That means, this vector below this you keep it this one, below that one keep a third column, below this one keep fourth column in this way, and you will get a matrix m into cross 1. Then Frobenius norm is nothing but a sum of absolute value of all elements square, sum of all elements square, square root of sum of all elements square. So, Frobenius norm is nothing but a, we denoted by this a m cross n of f stands for Frobenius norm is equal to summation of I is equal to 1 to m, summation of j is equal to 1 to n, m is the number of rows, this one, and a I j square. So, absolute value is not necessary, because it is a square of that one. This summation of all elements you take it, then take the square root of this one. So, it is like, if you see, it is like is what L2 norm. It is L2 norm of a matrix. You can say L2 norm of a matrix. Just like L2 norm of a vector, it is L2 norm of a matrix, is called the Frobenius norm. Next is your that L1 norm of a matrix. The same as the L1 norm of a vector. So, that is denoted by a m cross n of 1 is equal to maximum j, then summation of mod a I j, this I is equal to, this is j, I is equal to 1 to m, and j is equal to what? 1 to n, because our dimension m cross n. So, you take j is equal to 1, I varies 1 to m, you calculate all summation, then j is equal to 2, means second column, all the elements absolute sum you do it. Third column j is equal to 3, third column absolute sum of all these things you do. Out of this, which column absolute sum is maximum, that is called the L1 norm of a matrix. So, this is nothing but a maximum column norm, column sum, maximum column sum. So, if your matrix, if you see what will the L1 norm, this column you absolute sum of this you do it, that column absolute sum of this all elements you do it, and in this way you proceed up to nth column. Out of this, which one is the maximum value, that will give you the L1 norm of a matrix. That is why it is called maximum column sum. Then L2 norm, L infinity norm, next is L infinity norm of a matrix. L infinity norm of a vector is what? We have seen L infinity norm of a vector, the maximum value of this element of a vector. Similarly, here also L infinity norm of a matrix m cross n is equal to this L infinity is equal to maximum I is equal to 1 comma 2 comma dot dot m, summation of j is equal to 1 to n absolute value I j this. Now, I is equal to 1, where is j is equal to 1 to n, that row, first row, I is equal to second row. Out of this, all row wise you sum out of the absolute sum, then what out of this, which row is the maximum absolute value of the sum, that is called the H infinity norm of a matrix, or it is that is called L infinity norm of a matrix. So, that is called your also called maximum row sum. This has a similarity with the L infinite norm of a vector. L infinite norm of a vector, what is telling? You take the absolute value of all the elements, agree, then you picked up which value, which element have the maximum absolute value, that is the L infinity norm of a vector. Agree? Similarly, here also you row wise you take the absolute value of this one, out of this which one is maximum, that is the L2 norm of a matrix. So, next is L infinity norm, sorry, L2 norm of a matrix is defined as A m cross n 2 is equal to lambda max A transpose A, then square root of that one. That means, A is a rectangular matrix. You see, A is a rectangular matrix, and if you do A transpose, that dimension is will be n cross m, and this dimension I know it is m cross n. So, it will be a square matrix n by n. So, n by n you will get the square matrix of that one, you find out the absolute maximum value of this matrix, agree, and take the square root of it. This is a symmetric matrix, all eigenvalues are will be positive, non-negative number. In other words, all eigenvalues are non-negative. Out of this, which eigenvalue is maximum, you take the square root of that one. So, this is nothing but a this lambda max means maximum eigen value of A transpose A. This will show later, this is nothing but a maximum singular value of the matrix A transpose A. This is nothing but a maximum singular value of the matrix A transpose A. So, this is all about the vector and matrix norm. What are the norms? We have a P norm, then a Frobenius norm is nothing but a L2 norm, agree, and this or you can do not write it this L2 norm, you write it Frobenius norm, and this is nothing but a L1 norm, H infinity norm, L2 norm, this. So, you take an example and verify all the norms how to compute example. And this is you can write it, it is equivalent to a L2 norm of a vector, the way you are doing, agree. The way I told you that whole elements of the matrix is whole elements of the matrix you convert into vector form, then find out that vector L2 norm. So, this is equal to L2 norm of a L2 norm of a vector. No, instead of you write it L2 norm of a vector, when the matrix elements are arranged into a vector form. So, do the example of that one x, we have a vector whose dimension is 4 cross 1 is given 0, minus 10, 2, 1, and A is given 1, 0, 0, 0, 5, minus 10, agree. So, find out, if you find out the one norm of a vector, one norm of a vector means sum of all elements absolute value, that will come 13, that means 10 absolute value, then 2 absolute value, 1 absolute value is 1, that will be 13. Then x2 norm is nothing but a square of this one, then 0 square plus 100 square, sorry 10 square, then 2 square plus 1 square whole, then square root of this one, that will come root over 105, agree. And next is infinity norm f a, that infinity norm, out of this which magnitude is maximum, that means that transpose you can write it, that will be the 10. And next is that your matrix A, matrix norm A, Frobenius norm. Agree? This one is you arrange in the all vector and sum of the all things, then it will be coming. If you see this one, and this will be summation of I is equal to 1 to 3, summation of j is equal to 1 to 3, then mod I 1 j square and whole to the power of this. This is the Frobenius norm. Agree? Frobenius norm. This is the Frobenius norm. Frobenius norm, and that value is coming near about 126 to the power of half. Then A1 norm, A1, that means one norm of a vector, L1 norm or one norm of a vector is equal to what? Maximum column sum. Maximum column sum is what? This is 1, this is 15. So, this will be a 15, or you can say maximum column sum. Then this is A2, A1 to infinity, A1 to infinity is your maximum row sum is 10, maximum row sum. Then L2 norm of a matrix, L2 norm of a matrix, what is this? Square root of lambda max A transpose A, that quantity, and this quantity A2 norm, this quantity, if you do the multiplication, this will come your 125 square root of this one, that this maximum eigenvalue of A transpose A is 25. So, that square root of this one will come 11.18. So, this is the example form how you will find different norms, L1 norms, L2 norms and L infinity norm, all this. And in case of matrix is a Frobenius norm is what? Is same as L2 norm of a vector. So, this is I will stop it here today, and next class I will discuss the what is signal and what is system, how signal norms, physical interpretation of signal norms and system norms, that we will discuss next class.